So here's where we're going to get into the nitty-gritty of what's really happening to create a pressure, for a gas to create a pressure on its surroundings. So the molecules in this room are in constant random motion, colliding with each other and with the walls of the container. So here's a collision of a particle. It could be, think of it as an oxygen molecule, O2, or nitrogen, hitting the wall. That creates, it's those collisions with the wall that creates the pressure on the wall. Just a lot of tiny little collisions with that wall. The particles also collide with each other, so they can hit each other, and that's what causes them to change their speeds. So this is a so-called Maxwellian distribution. So on the horizontal axis is the molecular speed. That's how fast the molecules are moving. On the vertical axis is the percentage of the molecules that are moving at that speed. So at room temperature, so room temperature is about 300 degrees Kelvin. At room temperature, you see that the most probable speed, where this percentage reaches its peak, is about 400 meters per second. That's fast. That's really fast. That's about 30 meters per second. That's about 700 or 800 miles per hour. We could do the conversion. 700 or 800 miles per hour. So somewhere, I don't know, airplanes, I think, travel at about that speed. So we're talking about a very high rate of speed of these molecules that are moving, bouncing around in the room. But notice that not only is there a peak here, but there are some that are traveling very, very slow, almost zero, and others that are traveling at a much higher rate of speed, 800, 900 meters per second. So this is the distribution of speeds that you can work out using kinetic theory. We won't work it out. But I wanted to show it to you so you can appreciate the fact that the molecules in the room are moving at different rates of speed, colliding with each other, colliding with the walls. Now, this speed right here is called the RMS speed, and that's going to become important in the next couple of slides. What that means is that well, to understand the RMS speed, the easiest way to think about it is to think about what the average speed would be. Well, if you look at the molecules in this room, some are moving to the right, some are moving to the left, and if you want to average out the speed, the average speed is going to be zero, because the ones moving to the right will cancel out the ones moving to the left. That's kind of embarrassing. So you need a better measure for an average speed, and what you do in that case is the root mean square speed. So what you do is you say, let me look at the squares of the speeds. So v squared. Well, if you're squaring the velocity, then you're always going to have a positive number, and you won't get the ones traveling to the right and traveling to the left canceling each other out. You always have a positive number. So then you ask what the average square speed is, and then you take the square root of that. That's the root mean. Mean means average, and S means square. Root mean square speed. And that one turns out to be important. So that's pretty close to the most probable speed, about 484 meters per second. Now what happens if you quadruple the temperature in the room? Take it up, instead of 300 degrees Kelvin, we're up to 1200 Kelvin. That would be hotter than an oven, and not super advisable for human habitation. But what happens is, as you might expect, when you raise the temperature, this is the absolute temperature that I raised to 1200 degrees, this distribution shifts to higher molecular speeds. The particles are bouncing around at a higher rate of speed. There's still a whole distribution of speeds, but they're bouncing around at a higher rate of speed. And the RMS moves up to about 967 meters per second. We'll see these numbers later on, so if you, in a couple of slides from now, 484 meters per second for 300 K, 967 meters per second for 1200 K. Just fix those in our brains. All right, so for an ideal gas if you take these ideas and you look at the distribution of these velocities and you calculate the force, the net force on the walls of the container due to these collisions of the molecules with the walls, you can use the impulse momentum theorem to say that you've got a molecule that comes and hits the wall, bounces off the wall. That impulse of the collision of the molecule with the wall transfers some momentum and creates a pressure on the wall. And so if you do that carefully, and it's done in the book, I'm not going to go through the full derivation here, this is what you find. For an ideal gas, and we need, and the derivation does involve the ideal gas law, the relationship between the average translational kinetic energy of each particle and the temperature of the gas is what we're interested in. So I could put a T under here to remind us that it's translational kinetic energy, not 1/2 I omega squared for rotational energy. It's just back from chapter 5 or 6, whenever it was, when we talked about 1/2 mv squared. That's all we're talking about. And we want an average. Well, that average kinetic energy is the average of 1/2 mv squared. But 1/2 is always a constant. We don't have to average over it. It's just 1/2. Mass is just a constant. And then v squared, we have to average that. But we already said that VRMS is the square root of v squared average. So VRMS squared is the square of the square root of v squared average. So this is just 1/2 mVRMS squared. That's this beast right here. So that little exercise is just to convince you that this is the average kinetic energy for the particles, noting that the speed is squared there. The result of this derivation is that average translational kinetic energy is equal to 3/2 kT. This is one of the most important, most fundamental, most basic results in all of physics. The relationship between the average kinetic energy of these molecules bouncing around in an ideal gas and the temperature of the gas. Very, very important. It's 3/2, it's K, that comes out of the ideal gas law, Boltzmann's constant, times the temperature. So this temperature governs what this average kinetic energy is going to be. It doesn't tell you what the kinetic energy of every single molecule in this room is. It only tells you what the average is, because some are traveling faster and they have a higher kinetic energy, and some are traveling slower and they have a lower kinetic energy. It just gives you an average. So here m is the particle mass, measured in kilograms, nothing fancy there. VRMS is just as we've described it before, the root mean square speed. It's the root of the mean, meaning average, of the square of the speed. K is Boltzmann's constant, and T is the Kelvin temperature. Okay, an example. which relates to the figure that we talked about before. Find the RMS speeds of a diatomic oxygen gas. That's O2. Two atoms of oxygen bound together to form a diatomic oxygen molecule at 300 Kelvin and at 1200 Kelvin. We first need to just solve this equation for this K, 1/2 m VRMS squared equals 3/2 KT for VRMS. So we want to solve that for VRMS. How do we do it? Well, first of all, I can multiply both sides by 2. That cancels these 2's. I can divide both sides by m. That cancels this m. And then I can take a square root. And that's what we see right here. Next, we just plug in the numbers. The 3 times Boltzmann's constant, 1.38 times 10 to the minus 23rd joules per Kelvin, times 300 Kelvin, that's the temperature that we're going to do, times the mass of a single oxygen molecule. What's that? The very first concept we talked about is the atomic mass scale. We said you could read the atomic mass off of the periodic table, multiply that by 1.66 times 10 to the minus 27 kilograms, and get the mass of a single atom. But in this case, we don't have an atom, we have a molecule. We've got 2 oxygens, and if you look up the atomic mass of oxygen in the periodic table, it's 15.999 for each oxygen atom. Times 2 gives the atomic mass of the oxygen molecule, diatomic oxygen molecule, times 1.66 times 10 to the minus 27. So this whole quantity here gives the mass of one oxygen molecule. There's another way to calculate that, and there's an example in the book. Let me just show you quickly another way to calculate that same mass. That same mass can be thought of in the other way that you read off numbers off the periodic table. 2 times 15.999 grams per mole. But that doesn't give you the mass of a single molecule. But if you want it, you can divide by 6.022 times 10 to the 23rd, this is Avogadro's number, particles per mole. The per moles cancel each other, and we get the number of grams per particle. This number, actually there should be a kilogram right here, because remember that U, that atomic mass unit, is measured in kilograms, 1.66 times 10 to the minus 27 kilograms. This calculation here is going to give a mass of one molecule in kilograms. This will give us a mass of one particle, or one molecule, measured in grams. And so we just have to remember that there's 1,000 grams in 1 kilogram. That'll cancel the grams and give us the result in kilograms. And lo and behold, it's amazing, this number will be exactly the same as that number. You can calculate them either way. I just thought I'd show you both ways of calculating them. 2 times 15.999 divided by 6.022 times 10 to the 23rd, and divided by another factor of 1,000 gives you the same as 2 times 15.999 times 1.66 times 10 to the minus 27 kilograms. Bingo. Plug the numbers in and you get an RMS speed of 484. And that's the one that we saw before that I asked you to kind of keep in your minds. For the RMS, root mean square speed of oxygen molecules roughly at room temperature. Well, what about at 1200 degrees Kelvin? That's 4 times the temperature, much higher temperature. And you plug in that 1200 here, put a kilogram there, and you get 967, which is the number that we talked about right here. 967, 484. So we haven't actually calculated this full molecular distribution, but we've found the most important number, which is the root mean squared speed. Okay. Nice question. Does a single particle have a temperature? So each particle in a gas has a kinetic energy. We've established the relationship between the average kinetic energy, 1/2 m v RMS squared equals 3/2 kT, and the temperature. Is it valid then to conclude that a single particle can have a temperature? The answer is no. Particles in the gas have very different kinetic energies. Some have a higher kinetic energy, others have lower. The only one that we really can say anything substantive about is the average kinetic energy is equal to 3/2 kT. So if each particle had its own temperature, then there would be a whole range of temperatures of the gas. But that doesn't make sense with the idea, it doesn't square with the idea of thermal equilibrium. It can only have one temperature when it comes to equilibrium. So the temperature, you have to think about it as characterizing the random thermal motion of the gas as a whole and not the individual temperature of each particle. Derive the total internal energy of a monatomic ideal gas. So we're going to now specialize to monatomic ideal gases, which oxygen is not. It's a diatomic ideal gas. It has 2 atoms forming a molecule. Monatomic means that there's only one atom by itself that's moving around. And the reason is that diatomic molecules have different degrees of freedom, have additional degrees of freedom than translational. A monatomic gas can move this way, and this way, X, Y, and Z. That's why you have a 3 here, 3 translational degrees of freedom. But diatomic molecules can also vibrate, and they can rotate. And those additional degrees of freedom give us more complication here. It's not that hard, but we're going to specialize to monatomic ideal gases. And we're interested in the total internal energy of such gases. That means that if you have a box of gas and you have n monatomic gas particles inside that box, and you want to know how much energy is contained inside that box, then you might say, well, that's not that hard because I know what the average kinetic energy, translational kinetic energy is for each one of those particles inside the box. Why can't I just multiply by the total number of particles to get the total energy inside the box? And the answer is that's exactly how you do it. So here's the average kinetic energy per particle times the total number of particles to give the total internal energy. Well, we know from the concept we just did that the average kinetic energy, translational kinetic energy of each particle is 3/2 kT. Here's n just coming along for the ride. Then we're going to do a little bit to recall that Boltzmann's constant was the ratio of 2 constants. And it's in this concept right here, 14-7. The Boltzmann's constant was R over NA. And remember, because R was 8.31, NA was a very big number. You divide by that very big number, you end up with a very small number for Boltzmann's constant. So I'm just using that previous result, and then I'm doing a little bit of hocus pocus here to say that the total number of particles divided by Avogadro's number, N over NA, what's that? And you say, well, isn't that just the number of moles? And I say, yeah, it is. That's concept 14-5. So I'm going to replace N over NA by the number of moles. And so this is the total internal energy of a monatomic ideal gas. So this gives us another kind of energy to deal with when we're trying to think about conserving energy. We can convert that random thermal energy associated with this random thermal motion of a gas into other forms of energy.